Hello students, welcome to the lecture of structure of atom. We had discussed about the three quantum numbers, that is the principal quantum number, azimuthal quantum number and magnetic quantum number. The last quantum number, that is the spin quantum number, is left. We will discuss that today and we will also discuss about the shapes and energies of various orbitals. So, let us start. We will start with spin quantum number. That is denoted by S, and this was proposed by George Uhlenbeck and Samuel Goldsmith. This is denoted by S. This can also be denoted as MS. Okay. So, N, L and M, these three were obtained from Schrödinger equation. Schrödinger's wave equation. But S is not obtained from Schrödinger wave equation. Now, these three quantum numbers determine the location of the electron. But it was later observed that few more energy levels should be there because the line spectra had some more finer structures which were not explained. So, to explain these finer structures, another quantum number was introduced, which is known as the spin quantum number. So, the concept behind the spin quantum number is like the earth rotates around its own axis. We know that, and it takes 24 hours to complete a rotation which causes day and night. Similarly, an electron, along with revolving around the nucleus, the electron also rotates around its own axis. That is called the spin of the electron. Now, spin of the electron can be in clockwise or anti-clockwise directions. According to this, one electron can have two possible spins. So, if this is an electron and this is its axis, then it can either rotate in the clockwise direction or it can rotate in the anti-clockwise direction. So, this is the clockwise spin and this is the anti-clockwise spin. Now, due to these two different spins of electron, there are two spin quantum number for each electron, or two spin quantum numbers possible in one orbital. Okay. So, these two spins are written like this: one upward spin and one downward spin. Okay. And these are mathematically denoted as plus half and minus half. So, if in an orbital there are 2 electrons in opposite spins, then the total spin will be plus half and minus half will make 0. So, 2 electrons can occupy one orbital and the stable conformation is with 2 opposite spins. So, this is the spin quantum number. So, 2 electrons having opposite spins cancel each other. So, for one orbital there can be 2 spin quantum numbers. So, if we sum up all the quantum numbers, so we have these conclusions. The first one was principal quantum number, that is n. N specifies the size and energy of the orbits, and N denoted orbits or shells. Okay. The second one was azimuthal quantum number, that is denoted with L, and it expressed the subshells. So, total number of subshells is n in an orbit, and the values can be from 0 to n minus 1. So, from these we had seen that for L equal to 0 we call this subshell as S, for L equal to 1 we call it as P, L equal to 2 is D, and L equal to 3 is F. The third one was magnetic quantum number. Magnetic quantum number M. So, this denoted the orbitals, and they described the orientation of orbitals in a subshell with respect to standard coordinate axis. So, the values, total number of magnetic quantum number will be 2L plus 1, and the values will range from minus L to plus L. So, we had seen like for P, since L equal to 1, total number of M will be 2 into 1 plus 1, that is 3. So, there will be 3 p orbitals with the magnetic quantum numbers minus 1, 0 and plus 1, which we called as px, py and pz. And now we learned that the fourth quantum number is the spin quantum number, which is denoted by S, and it describes the orientation of the spin of the electron. That is plus half and minus half. Now, if we take one example, suppose 3p, okay. So, in 3p, we have n equal to 3. This is the principal quantum number. Now, azimuthal quantum number L equal to 1 for p. So, the m will be minus 1, 0 and plus 1, and we draw the p orbitals like this, minus 1, 0 and plus 1. Now, one orbital can contain maximum of 2 electrons. So, now the p orbital can contain 6 electrons. So, we can write like this. So, each orbital can have 2 electrons with the opposite spin. 2 opposite spins are the stable conformation. So, if this is plus half, then this is minus half. So, now we know about the 4 quantum numbers. Now, we have discussed about the various orbitals. Now, we need to know that what are the shapes of these orbitals. So, now we will start shapes of orbitals. So, first of all, the region around the nucleus where the probability for finding an electron is maximum is called orbital, right? So, in an orbital, the probability density psi squared is maximum. Now, the region where probability of finding an electron is 0. That is called node or nodal surface. Okay. So, here psi squared is 0. Now, from this we will predict the shapes of orbitals. So, first shape of s orbital, m equal to 0. Now, shape of s orbital L equal to 0, right. So, if L equal to 0, then m will be 0 because there is no minus L or plus L. So, S has only one orbital which we represent with a single box. Now what is the lowest n possible for s orbital? So n equal to 1, because we know that maximum number of L that can exist within a principal quantum number is n minus 1. So 1 minus 1 is 0, therefore 1s is the lowest s orbital. Okay. Now we need to know certain points, that the probability density or the probability of finding an electron is maximum near the nucleus. And decreases as we move away from the nucleus. So with this factor, we will plot psi as a function of r and psi squared as a function of r. Now if we plot for 1s, we see if this is, so we see that the graph comes like this. This is 0. Okay. So this is psi versus r for 1s. Now if we plot the probability density, psi square as a function of r, then this is like this. Okay, this is the plot for 1s. Now these lines will not actually become 0, it will come like this. Similar for here, it will continue like this. So these are the plots for 1s. Now if we plot for 2s, then if we plot psi r versus r for 2s, we see that this plot is like this. Okay, and because since psi is square, for psi square, since this is a square term, it will never be negative, because the square of the negative value will also be positive. So these are the plots for 1s and 2s. So for 1s, we see that the graph of probability density, or for the graph of probability, it never touches 0. It continues. So for 1s, there is no node. For 1s, no node. Okay. For 2s, we see that the probability density once touches 0, then again increases, reaches a small maxima, and then decreases, and it continues. So for 2s, we can see one node. Okay. So, we will discuss about the detailed shape of the s orbitals and other orbitals in the next part. Thank you.